I'm Professor Rad, and this is Precalc video 325, solving trig equations using substitution. In this video, we're going to work through two examples where we use substitution to help us solve the equation. Now, substitution is a technique that's often used in calculus when you have a really complicated looking function and it's difficult for you to see the big picture because of all those messy details. And so substitution can kind of help us rewrite and reframe a problem in a way that's going to make a little bit more sense. So the methods that we use on these examples here not only help us to solve trig equations, but they also help us to become familiar with this concept of substitution, especially the concept of substitution with regards to boundaries of values. That's going to help with some substitution in integration in the future. So let's go ahead and work through these two examples and see how this is going to work. So we're going to solve the equation 2 cosine of 3x minus pi eighths, plus root 2. This would be helpful if it's a true equation, meaning it should be equal to 0. Forgot the equals part there, on the interval from 0 to pi. So we're going to start solving this one just like we've solved all of the other trig equations so far by isolating the trigonometric expression. So we want to get cosine of the mess equal to something. So let's begin by subtracting root 2 from both sides. So we'll get 2 cosine of 3x minus pi over 8 is equal to negative root 2. And then let's divide both sides by 2. So that will give us cosine of 3x minus pi over 8 is equal to negative root 2 over 2. Now from here, we could draw a unit circle and try and find all places where cosine is negative root 2 over 2 and use that to get some expressions and then set up some equations and solve for this. One of the difficulties in doing that is that we have an interval for x going from 0 to pi, but we don't have an interval for this expression. So one way that the substitution is going to help us is it's going to help us know what interval we're looking at for our solutions. So here's how the substitution is going to work. Instead of thinking of this problem in terms of x's, I'm going to call this some other value. So let's call that theta so that we have an angle to work with. So ultimately, our goal is going to be to solve, ultimately our goal is to be to solve for x. But when we do the substitution, we're going to have cosine of theta is equal to negative root 2 over 2. And we have to figure out the interval that we're going to be looking at. So if we can figure out what interval we're looking at, that will give us an interval for us to find theta. And then we know, how far to do the swirl around our unit circle to know where our solutions are going to be. So to help us find this interval, we're going to have two steps. So step 1 is we're going to rewrite this as an equation, and then we're actually going to solve it for x. So step 1, we're doing the substitution where theta is 3x minus pi over 8. And we're going to solve this for x. So we're going to add pi eighths to both sides. And then we can multiply both sides by 1/3 or divide by 3. Either way, we'll get theta over 3 plus pi over 24 is equal to x. Now, the reason we want to do that is because we have this interval for our values of x. So we know that x is in between 0 and pi. So our second step here is to write that in inequality notation. So we're going to have that x is between 0 and pi. What we would like to do is to get an interval for theta. So the reason we took this theta equation and solved for x is so that I can now replace x with this theta expression, and then that will give me an interval for theta. So I'm going to replace x with theta over 3 plus pi over 24. So now I'm doing this replacement so that I can then solve this equation for theta, or inequality rather, solve this inequality for theta. So let's start out by subtracting pi over 24 from everything. And then we can multiply everything by 3. So since 3 goes into 24 8 times, that will give us negative pi over 8 up until 23 pi over 8. So what this means is when we go to find our solution, we want to be looking at values that are between negative pi 8ths and 23 pi 8ths. So we have negative pi over 8 and 23 pi over 8. Okay, so let's step back and recap what we've done so far, because it might be it's a little bit strange the first time you work through it. So to recap, we solved this equation for cosine. And then instead of dealing with this mess, we said, let's call this theta. So really we're solving cosine of theta is negative root 2 over 2 on some interval. So we needed to figure out what interval that was going to be. So we took this expression, or this equation here, where theta is 3x minus pi 8ths, and we solved that for x, so that we could then use the boundary of x to come up with a boundary for theta. So now we've taken this messy equation and turned it into a little bit of a more simplified equation. Once we have that, now we can go ahead and find the solutions to this equation. So cosine is negative root 2 over 2. So I know root 2 over 2 is going to involve 45 degrees, or pi fourths. I'm just going to dot those in. And if cosine is negative, cosine is going to be negative in quadrants 2 and 3. So I'm going to be looking at this angle here and this one here. Okay, so now I know where those values are. Next, it's going to get tricky to see where the spiral starts and ends. So it's going to start at negative pi over 8. Now, it might help me to draw in the pi 8ths to count them. Now, pi 8ths, an eighth is half of a quarter. So since we have our quarters drawn, we could draw each of those in half to get eighths. So why don't we do that? This is just to help me visualize where those eighths are going to be. So negative pi over 8 is this one here. So my first spiral is really tiny because it's just bloop, from 0 to negative pi over 8. And there are no solutions there, so I'm not going to worry about that. Then we have to go to 23 pi over 8. So I know that this is 8 pi over 8. If I go over here, and then another 8 is going to bring me to 16 pi over 8. And then another 8 will bring me to 24 pi over 8. So if I go around the unit circle 1.5, that's 24 pi over 8. And we want 23 pi over 8. So we're going to stop 1/8 before. So we're going to go all the way around and then almost halfway again. So this is my 1 pi, 2 pi, and then up to 23 pi over 8. When I check this spiral, I'm going to hit here, here, and here. So we're going to end up with 3 solutions for theta. So remember, we're counting now. These purple lines are all in reference to the pi 8ths. That was to help me draw the spiral. When I'm counting the fourths because that's what my solutions were on. The solutions were on the quarters. So this is 1 pi fourth. So this is 1 pi fourth, 2 fourths, 3 fourths. So that's this first dot. It's going to be 3 pi over 4. 4 pi fourths, 5 pi over 4. 6, 7, 8, 9, 10, 11. All right, so we've now got our 3 values for theta that were in our transformed interval. Our last task is to now take these thetas and transform them back into x's. So we have this equation for x. X is theta over 3 plus pi over 24. So we're just going to replace theta with each of these 3 values. And since it's over 3, I think I'm going to think of this as 1/3 times theta, just to make the simplification a little bit easier. So I need some more space. So we'll get rid of that part. And sure, let's get rid of this. So when theta is 3 pi over 4, that means that we're going to have x is equal to 1/3 times 3 pi over 4 plus pi over 24. So let's see. That's going to give me pi fourths plus pi over 24. So that is going to be 7 pi over 24. Okay, so we figured out this first piece. For the next one, when theta is 5 pi over 4, that means that x is going to be 1/3 times 5 pi over 4 plus pi over 24. So let's see, this is going to be 5 pi over 12. So that's 10 over 24 plus 1 is going to give us 11 pi over 24. We figured out that one. And then for the last one, when theta is 11 pi over 4, that means that x is going to be 1/3 times 11 pi over 4 plus pi over 24. So this is 11 pi over 12. So 22 over 24 plus 1 is going to give me 23 pi over 24. Whew. All right, so that means that these 3 values here are our values for x. And if I check, they're all between 0 and pi. So my final solution is going to be the set of 7 pi over 24, 11 pi over 24, and 23 pi over 24. And of course, if you want to check your answers, you can throw them into a calculator. So actually, why don't we do that? I'm just going to check one of them just as a justification here. Why don't we check this one in the middle? So I'm going to throw these values into the original equation. So I'm going to do 2 times cosine of 11 pi over 24 times 3. Let me rewrite that, 3 times 11 pi over 24 minus pi over 8 plus the square root of 2. And here's hoping I get 0. Yay, I got 0. So if you didn't get 0 when you do your check, first check to make sure your calculator is in radians and not degree mode. And then if you get something that doesn't work, then you can go back and check this process. And if this process is correct, go back and check our solutions for theta. And if our solutions for theta were correct, go back and check this process here. So there are a lot of places where we can make a mistake. So you want to take your time on each step of the process. So what I'm going to do is, I said we were going to do 2 examples together. What I will do is I'll put another problem on the board that you can try for practice, and then you can pause the video and work through that. And I'll write my solution to that one on the board in case you want to check your work for that. So let's go put a practice example on the board. Okay, so here's an example that you can work through. I'm going to kind of guide you in stages and just put some answers on the board so you can check your work if you want as you go along. So our equation is to solve 1/2 secant of 5 theta minus 3 pi over 2 equals 1. And we're going to solve that on the interval from 0 to pi halves. So for your first step, you're going to pause the video and see if you can solve for secant of 5 theta minus 3 pi halves. So pause the video and see if you can work through that. And then when you think you've got that part done, unpause and check your answer and then move to the next step. All right, so that first step actually isn't too bad. All you have to do is multiply by 2, right? So if you multiply both sides by 2, you end up with secant of the mess is equal to 2. So for the second step now, we have a few more stages to do. We're going to do, this is the substitutionary step. So we're taking that mess and we're just calling it one thing. I decided to call it phi. If you want to call it x, that's fine. Call it anything other than theta because theta is already in play. So this is going to be our substitution. So for your next step, try to solve for theta. So pause the video, solve for theta. When you think you've got it, unpause, and we'll have the answer for you to check, and then you can move on to the next step. All right, so for step 2, you should have gotten that theta was phi over 5, or 1/5 phi, plus 3 pi over 10. So if you didn't get that, pause and check your work. Once you get that, then we can move on to step 3. So we're going to use our boundaries here, that theta is between 0 and pi halves, to find boundaries that involve phi. So once again, go ahead, pause the video, see if you can figure out the boundaries for phi, and then you can unpause and check, and then move on to the next step. Alrighty, so for step 3, I got that phi had to be between -3 pi over 2 and pi. So once we've transformed our boundaries, we can move on to step 4, and we're going to solve secant of phi equals 2. So what we've done is we've just replaced the mess with phi. So we have secant of phi equals 2, and we're going to solve it on this new interval. So see if you can find the solutions for that. There should be 2 solutions on that interval. All right, so hopefully you took the time to pause and work through this one. So if secant was giving you trouble, remember you can always turn that into cosine. So you would have cosine of phi is equal to 1/2. So you can use that to help you out. And I got a solution of -pi3 and pi3 for that. So now that we have our solution for phi, the last step is to turn the phi's into thetas. So go ahead and see if you can use your equation for theta, which we found earlier in step 2, to help you find your values for phi. And then once you've got it, you can unpause and we'll check our answers. All right, so our final solution should be that theta is equal to 7 pi over 30 and 11 pi over 30. If you substitute these into the original equation, they should check out. And because our values have to be between 0 and pi halves, we want to make sure we check that as well. So because both of these have a denominator of 30, I can rewrite pi over 2 as 15 pi over 30. So both of these are between 0 and 15 pi over 30. So we're within the correct window. All right, so hopefully this example gives you a little bit more practice on the different steps of this involved process. Let's do another example together that's going to have one more step at the beginning, and then it's going to flow very similarly to this one. For this example, we're going to solve the equation sine of beta minus √3 cosine beta is equal to 1. Now, This is one of those kinds of equations that we saw in the last video, where the more of these you work on, the more adept, the more your eye is going to see certain things. So one of the difficulties of this equation is that we have sine and cosine. Now, if we had sine squared, that would be good, because then we could use the Pythagorean identity to write it as cosine squared. But we don't have sine squared, we have just sine. And same thing, we don't have cosine squared, we have just cosine. So instead of using a Pythagorean identity to help us out on this one, we're going to use a sum or difference formula to help us out. So what I'm noticing here that helps me recognize that is that the coefficient of the sine is 1. The coefficient of cosine is √3. And I know that I have a pair on the unit circle that has 1/2 and √3/2, or √3/2 and 1/2. I know that those are points on the unit circle. So if I were to divide by 1/2, I would get that pair 1/2 and √3/2. So that's what I'm looking for here. I'm looking for one coefficient to be √3 and the other one to be 1. That's kind of the trick on this one. So let's divide everything through by 2. And we end up with 1/2 sine beta minus √3/2 cosine beta is equal to 1/2. Now, here's why this is helpful. It may look like we just made it worse because we just threw fractions into here, but this is actually going to help us to solve, because we have that pair 1/2 and √3/2, whichever way we feel like thinking about it. Either one's going to be fine for this. We can think of this as having cosine sine and then sine cosine. So remember that our sum and difference formulas were cos, cos, sine, sine, and they had sine, cos, sine, cos. So these values here represent a sine and cosine pair. So let's see, if I want to have a sine cos and a cosine here, then this means this would have to be cosine, and that's going to be cosine of what? So cosine of pi3 is going to be 1/2, and sine of pi3 is going to be √3/2. So we're using this one here, where the x value is 1/2 and the y value is √3/2. So I can think of this equation now as cosine of pi3 sine beta minus sine of pi3 cosine beta is 1/2. So now we have this setup of sine cos, and notice that we have sine of beta, sine of pi3, and we have a cosine of beta and cosine of pi3, so that's what we need to have. So we have sine cos, same. So that means this is going to be a difference formula for sine. So this whole expression is going to become sine of beta minus pi3 is equal to 1/2. So remember that when we have a sum or difference formula for sine, it turns into sine cos, sine cos, same. So I'm starting out with sine cos. So sine of beta comes first. And then pi3 is the cosine argument. So that's going to come second. So basically what we've done here is we've done a difference formula in reverse. We're accustomed to starting here and working our way up towards something like that. So now we've gone in reverse. We've sort of retroactively turned it into this expression. But the good news is that now we have sine of something equal to 1/2. So we can let the something be theta. So after we define theta, we also need to define beta. So this one's not going to be that terrible to solve for, right? So we have theta is beta minus pi thirds. And we can solve for beta just by adding pi thirds. So that will give me theta plus pi thirds is equal to beta. All right, so we have our equation for theta. We have our equations for beta. So now we just have to adjust the endpoints of our interval. We don't have interval endpoints, guys. So this equation didn't give us a definite domain to solve on. So the good news is we don't have to worry about adjusting the endpoints of the domain. We just have to adjust our starters and adjust our periods accordingly. So in this case, since we have sine of theta is 1/2, let's just go ahead and solve that for theta. So I'm going to draw my unit circle here for reference. Sine is going to be the y value. So y is 1/2 here at pi over 6. And it's 1/2 here at 5 pi over 6. So that means we are getting two solutions or two base solutions for theta. Theta is pi over 6, or it is 5 pi over 6. So since we have these values for theta, we can go ahead and throw them into this formula, which was for beta. So we can get beta by adding pi thirds to theta. So I'm just going to do that here. Okay, so a pi third, that's 2 pi over 6. So it's going to give me 2 plus 1. That gives me 3 pi over 6, which is pi over 2. And 5 pi over 6 plus 2 pi over 6 is going to give me 7 pi over 6, which doesn't reduce. So that's where we're at. So that means that beta can be pi halves or 7 pi over 6. And let's go ahead and look at this equation that we were solving. So this equation that we're solving here with the beta, the omega value is 1. So the period of this function is still 2 pi. So putting these solutions for beta together with the period, we're going to get the final solution of set of all theta, so that theta is equal to pi halves plus 2k pi, or theta is equal to 7 pi over 6 plus 2k pi, where k is an integer. And there we go. That's going to be our solution for this equation. Hey, editing Professor Rad here. I did want to mention one more thing. So in this example that we just did, we had sine of beta minus √3 cosine beta. And we used this ordered pair here to help us out. So the coefficient of sine was 1, the coefficient of cosine was √3. So this 1 and this √3 gave us guidance to use this point to rewrite the equation so that it looked like this. What I wanted to point out is that there are other ordered pairs on the unit circle that can help us out in different situations. So for example, suppose we had this equation here, where instead of having a √3 as our coefficient to cosine, we just had a 1. So in this instance, the coefficients of the sine and the cosine are the same. So to help us out, we would need an ordered pair on the unit circle where the sine and cosine values would be the same. So a point that would have the same x and y values. So what would work in this case would be √2/2 and √2/2. I mean, you could also use negative √2/2 and negative √2/2, I guess, if you wanted to, but why make things overly complicated, right? So just like before, we needed to divide everything by 2 to get that 1/2 and that √3/2 as coefficients. On this example, we would multiply everything through by √2/2 to get √2/2 as a coefficient. So now I have √2/2 sine beta minus √2/2 cosine beta. And then I just had to multiply the right by √2/2 as well. So now, just as before, we were able to look at sine of pi thirds and cosine of pi thirds. We can use, we can think of this as either sine or cosine of pi fourths and either sine or cosine of pi fourths. So actually on this one, it doesn't matter because we have the same x and y values. So if we wanted to call this one cosine of pi fourths and this one sine of pi fourths, we could. I did choose to do it a different way on this one, just to demonstrate a different thing that can happen. So I decided to call this one sine of pi fourths and this one cosine of pi fourths. I wanted to do this to illustrate that now we have sine, sine, cos, cos. So we no longer have the sum or difference of a sine function. So remember, sine sum and difference is sine, cos, same, and cosine sum or difference is cos, sine, opposite. So here we're having something closer to a cosine sum or difference because we have cos, and sine. They're just in the wrong order. So I'm going to rearrange it so that the cosine expression comes first and then the sine expression comes second. But now we have a problem that cosine has a negative in front. So let's just divide everything by a -1. And aha, here we go. So now we have cos, sine, and then we have a negative √2/2 because we divided through by a negative. So now with that little bit of work, we have cos, sine, opposite. So we can write this as cosine of the sum. So we have pi fourths and beta. So we have pi fourths and beta. And the opposite of subtraction is addition. Oops, I have a little typo here. This should be a negative √2/2. Sorry about that. But this is essentially what we would, another way of using a sum or difference formula for a problem like this one. So if the coefficients are the same, then you would use √2/2. And if they were different, like 1 and √3, then we could use the 1/2 and the √3/2. If we had something that didn't resemble anything on the unit circle, well, then we're going to have to use a different technique. And I'm going to stop this interruption here, but you would then go ahead and you would solve this equation just with a negative √2/2, the same way we did the example on the board. Okay, I'm going to stop interrupting now and let you go back to your regularly scheduled video. All right, so I know that this video had a lot in it. The substitution tends to be a little bit of one of those topics that makes our head hurt a little bit because we are generalizing and we're kind of learning a new process in the context of these equations, which are already fairly, difficult. So it's okay. Make sure you take a break and then go ahead and see if you can retry the examples and see if it sinks in a little bit better second time through. So hopefully this video did help a little bit in using substitution to solve trig equations. In our next video, we are going to look at solving trig equations using a calculator. So those will be situations where our properties fail us or something like this isn't going to work too great. So I hope you have a magnificent day and I'll see you next time. Bye for now.